All right, here we're looking at section 11.5, and our learning targets for today are to estimate population parameters. Then we're going to be analyzing those estimated population parameters, and because remember we can never find an entire information about populations, so we have to estimate them. So we're going to be analyzing some data, and then we're going to find the margin of error for surveys. So when we're dealing with statistics, we have two major branches. We have descriptive statistics and inferential statistics. We've really been dealing with descriptive statistics so far. That's where we organize, summarize, and display our data. So we're also going to be looking at some inferential statistics where I take a sample to draw some conclusions about a population. So I can use these statistics to make reasonable predictions or inferences, right? Because I'm not telling everything about the population. I'm using my sample to get some ideas about it. So that's my inferential statistics. So here's our first example. The numbers of friends for a random sample of 40 teen users of a social networking website are shown in the table. Estimate the population mean. And this is another Greek letter. This is mu, and this is going to always be our population mean. It is always this Greek letter. So in order to estimate that population mean, I have to find my sample mean. And in order to find the sample mean, here's the kind of formula I do. The x with the dash over it is always my sample mean. And remember, I'm using a sample because I can't gather the entire population. This is sigma. This tells me the sum of all of my values, all of my x values, divided by the number of values that there are, right? Just finding any normal mean. So if I add up all of these values, all of them, I end up with 11,966, and I divide that by 40 because there are 40 different values here. So I end up with my sample mean of 299.15. So the mean number of friends for all teen users of the website is about 299. So I take this sample mean and I can use it to describe my population mean. And that's true for most data that we're going to be looking at. So here's your first monitoring progress. Try it and see if you can come up with the right answer. The biggest thing with using this much data is make sure that you're very careful when finding the sum, that you don't miss a number or mistype it in your calculator. So here's our second example. So a student newspaper wants to predict the winner of a city's mayoral election. Two candidates, A and B, are running for office. 8 staff members conduct surveys of randomly selected residents. So here I'm told it's a random sample, so I know that I can continue with my study. The residents are asked whether they will vote for candidate A. The results are shown in this table. So I've got my sample size, right, because I'm dealing with different sample sizes and a different number of people voting for candidate A. Then we've also found the percentage by just dividing the number of votes by the sample size. And we can see that the larger the sample size gets, the closer my data gets together. And that's true for all data. That's why we like very large sample sizes. So now here comes our questions. Based on the results of the first 2 sample surveys, do you think candidate A will win the election? Explain. So of my first 2 sample surveys, I didn't have very large groups, and I did not have very positive results for this survey. So fewer than 50% of my residents of those first 2 would vote for candidate A. So I would say that no, I don't think that A is going to win the election. So now let's look at part B. Based on the results of the entire table, do you think candidate A will win the election? And explain that. So as my sample size increases, the estimated percent of voters approaches 59%, right? We get closer together and closer to our final answer. So that from this, with my large sample size, I would say that I could predict that 59% of the city residents will vote for candidate A. So since I need more than 50% to win, I would say that candidate A will win that election. So I always, when I'm dealing with numbers, I always want to look at my sample size and know that the larger the sample size, the more accurate my data will be. So now go ahead and think about this one. So here's our next example that we're going to be looking at. We're going to be analyzing some data here. So a national polling company claims 34% of U.S. adults say mathematics is the most valuable school subject in their lives. You survey a random sample of 50 adults. So what can you conclude about the accuracy of the claim that the population proportion is 0.34 when 15 adults in your survey say mathematics is the most valuable subject? Then I'm going to say, what can you conclude about the accuracy of the claim when 25 adults in your survey says math is the most valuable subject? Then I'm going to assume that the true population proportion is 0.34. So estimate the variation using sample sizes of 50. So the first thing I want to think about is I looked at this in previous sections. I'm looking at a claim, so I'm also dealing with this hypothesis. So the hypothesis is that the population proportion of U.S. adults who say mathematics is the most valuable school subject is 0.34. So to analyze this, I make a simulation like I've done before. So I choose 80 random samples of size 50 using a random number generator on my graphing calculator. There are also random number generators online as well. So first I generate 50 random numbers from 0 to 99 for each sample. Any number between 1 and 34 represents an adult who says math. So then I can find my sample proportions and make a dot plot showing my distribution. So I go and I plug that into my calculator to find my random numbers, and then I make my dot plot. So here's my simulation of polling 50 adults and seeing my random samples. And this is the proportion of 50 adults who say math, right? We're dealing with all proportions here. So then I can look at my dot plot and answer my final questions. So 15 out of 50 corresponds to a sample proportion of 0.3, so that corresponds to this line in my dot plot. In this simulation, the result occurred in 7 out of my 80 random samples, right? So it's likely that 15 adults out of 50 would say math is the most valuable subject. So I can conclude that the company's claim is probably accurate, and because that falls near the middle. So now let's look at part B. So 25 out of 50 correspondence was my 0.5, so I can look at my dot plot and see that this is over here. So in the simulation, this occurred in only 1 of my 80 samples, so that it's unlikely, right, because this is a very low percentage, it's unlikely that 25 adults out of 50 would say math is the most valuable subject, when my true population percentage is 34. So using this information, I would say that the company's claim here is not accurate. And then for C, I'm analyzing what my plot looks like. So this is pretty bell-shaped and symmetric, so my distribution's almost normal, right? And we've talked about normal is that inverted bell curve. So in a normal distribution, 95% of the proportions lie within 2 standard deviations of this 0.34. So excluding the 2 least and 2 greatest sample proportions represented by the red dots, right? It's the 2 smallest and the 2 largest. I get rid of those. That leaves 76 out of my 80, which is 95% of my sample proportions. So these 76 proportions range from 0.2 to 0.48. So 95% of the time, a sample proportion should lie in that interval, just using the information I know about normal distribution curves. So now I want you to think about this problem. It's dealing with that last example, and see what you can think about this one. So now we're going to be looking at margin of error. So a margin of error gives a limit on how much the responses would differ from the responses of the population. So since we're dealing with samples, we can't say that the entire population would guess that, so we have to use a margin of error. So here's my formula that I use. So when a random sample of size n, so n is my sample size, is taken from a large population, the margin of error is approximated by the margin of error equals plus or minus 1 over the square root of n, and n is my sample size. So this means if the percent of the sample responding a certain way is p, so p is going to be that decimal, so my population respond would fall within this range, right? So I'd have the population minus the margin of error, and I would add the margin of error. And we'll see this in examples coming up here. So let's look at this. In a survey of 2,048 people in the U.S., 55% said that television is their main source of news, right? And we can see this based on this graph. What is the margin of error for the survey? Then we're supposed to give an interval that is likely to contain the exact percent of all people who use television as their main source of news. So the first thing I have to do is find the margin of error. So to do that, I use the margin of error formula. So I find the margin of error. I have plus or minus 1 over the square root of n, and n is that survey size. So I just substitute that 2,048 as my n, and then I use my calculator to see that my margin of error would be plus or minus 0.022 or 2.2%. So now to find my interval that includes everybody, I would add and subtract this 2.2% to the people that selected television. So I'd have my 55 minus 2.2%, which gives me 52.8%. And then I add it, so 57.2%. So it's likely that the exact percent of all people in the U.S. who use television as their main source of news is between these two values. And you'll notice that when my sample size is extremely large, my margin of error gets much smaller. And that mathematically makes sense because the more people I survey, the more randomness I get in there, the more closely I get to an entire population statistics. So try this one and see how you can do. We're really going to be using margin of error a lot, so we want to make sure that we know how to find it and how to go back and forth with it. So our learning targets again were first we had to estimate population parameters, and to estimate these parameters we used some data from a sample group and found some of their means. Then we looked and analyzed those estimated population parameters, and then finally we found a margin of error for surveys. And this margin of error can be used also to find the number of people that were surveyed if we know the margin of error. So now that we've worked on these learning targets and talked about all of them and seen examples, go ahead and work on your homework for 11.5.